Now let's do some of our review problems for our electrostatics. Remember, these problems are due before the test, B-E-F-O-R-E. Okay, make sure you can do any problem in this packet. Now, what is the force between two charges, 3 times 10 to the negative 23 coulombs and 7 times 10 to the negative 7 coulombs, if they're 0.05 meters apart? Well, make sure you give me your givens. Q1 is 3 times 10 to the negative 23rd coulombs. Q2 is 7 times 10 to the negative 7 coulombs. And the distance between them is 0.05 meters. So the force that you're looking for, here's your unknown, is K Q1 Q2 divided by D squared. So it's 9 times 10 to the 9th. Q1 is 3 times 10 to the negative 23rd coulombs times 7 times 10 to the negative 17. I forgot my 17 there, guys. Coulombs divided by the distance, which is 0.05 meters, and that's squared. So you get 7.56 times 10 to the negative 17 newtons. So this is straightforward finding the force between any two charges, Q1, Q2. Now remember, because these two have the same sign, the force is repulsive. So this is a force of 2 on 1 and the force of 1 on 2. They repel each other. Now what is the distance between two charges? If the force is 6.2 times 10 to the negative 2 newtons, and the charges are 5 times 10 to the negative 23, and 4.2 times 10 to the negative 15. Well, this is Q2, Q1, this is Q2. So I have F is 6.2 times 10 to the negative 2 newtons. Q1 is 5 times 10 to the negative 23 coulombs. Q2 is 4.2 times 10 to the negative 15 coulombs. So I know that I'm looking for D. So I know F is K Q1 Q2 divided by D squared. I need to solve this for D squared. So the first thing I'm going to do is multiply through by D squared, both sides. Let me go back to black. So F D squared is K Q1. I don't know why I'm making G's this morning. Q2. I still want D by itself. So I need to divide through by F on both sides so that I wind up with D squared is K Q1 Q2 divided by F. Now in order to get D by itself, because D is squared, I need to square root both sides. So D is the square root of K Q1 Q2 divided by F. All right, now you plug in. So this is the square root of 9 times 10 to the 9th. Q1 is 5 times 10 to the negative 23. 4.2 times 10 to the negative 15 divided by the force, which is, what was my force? 6.2 times 10 to the negative 2. Now go on and type these in. All right, 9 times 10 to the 9th times 5 times 10 to the negative 23 times 4.2 times 10 to the negative 15. And you get a numerator of 1.89 times 10 to the negative 27 divided by 6.2 times 10 to the negative 2, and you have to square root that. Now do this division right here, times 10 to the negative 2. So you get that what is under here is we're getting the square root of 3.048 times 10 to the negative 26. And now you square root that. It's important you do these steps kind of in this order so that, and lo and behold, you get your algebra correct. So this becomes 1.75 times 10 to the negative 13 meters. Distance is in meters. So we need to change that to meters, don't we? Goodness gracious. A couple mistakes on this review sheet. Sorry about that. What do we do? We'll do this. Do it like that. All right. Getting carried away here. Now, what is the unknown charge? So we're looking for Q2. If there's a force of 10 to the negative 3 newtons, so F is 1 times 10 to the negative 3 newtons on two charges that are 0.0004 meters apart. So the distance is 0.0004 meters. And your second charge, or your first charge, is 5 times 10 to the negative 15 coulombs. It doesn't matter which one you call it, Q1 and Q2. So we're looking for Q2. So I know that F is K Q1 Q2 divided by D squared. So we want Q2. So we need to get rid of D squared from both sides. This becomes FD squared is K Q1 Q2. Again, we're still looking for Q2. So we've got to divide this by KQ1. So Q2 is F D squared divided by K Q1. So now we're going to come up here and plug this in. Q2 is the force, which is 1 times 10 to the negative 3 times D squared, so it's 0.0004 squared divided by, let's see, K is 9 times 10 to the 9th, and Q1, let's see, the first charge is 5 times 10 to the negative 15. Now this is important. Go ahead and do these calculations separately. 1 times 10 to the negative 3 times 0.0004 squared is, pick up my pen, 1.6 times 10 to the negative 10. And then we're going to divide that by, we're going to multiply straight across now. So now I'm going to multiply 9 times 10 to the 9th and 5 times 10 to the negative 15. And I get 4.5. Here we go. 4.5 times 10 to the negative 5th. Now I'm going to divide 1.6 times 10 to the negative 6 by 4.5 times 10 to the negative 5. And I get a weird answer. Let me do it again. 1.6 times 10 to the negative 10 divided by 4.5 times 10 to the negative 5. And I get 3.55555. So let's just round that to 3.56. That's not a very good one. Let's start over. 3.56 times 10 to the negative 6. Always check your numbers that you put in your calculator. You never, teachers make mistakes. So, all right, two charges are separated by distance d and exerted force F. What will happen to the force if we, let's say if Q1 and Q2 are cut in half? Let me write my formula. F is K Q1 Q2 divided by d squared. You see how I put spaces there? Now what are we doing to this? Q1 and Q2 are cut in half. So it's going to be half of Q1 and half of Q2. Now what happens when we do this? 1/2 times 1/2 is 1/4, my original force. What do we do if D is cut in half? Do the exact same thing. F is K, Q1, Q2 divided by D squared. Don't forget your squared. That's kind of important on this one. Now, if D is cut in half, we wind up with 1 divided by, now 1/2 squared is 1/4. Okay? Now remember how you divide fractions by fractions? You invert and multiply. So this is going to be 1F invert 4 divided by 1 and multiply. So there's your time. So it just becomes 4F. Sketch electric field lines around the following. Now, if you have a positive charge, remember they start on positive. Okay, and if it's 1 point, it just goes radially outward. This one, I gave you an actual value of the charge, but it doesn't really matter. It would be the exact same diagram as just a 1 coulomb charge, unless we were comparing them. Down here, a dipole always starts on positive, ends on negative, and these are going to curve. Make sure you get the shape of these. There should be the same number on the positive as a negative. Make sure your arrows land on negative and point away from positive. What's the magnitude of the electric field? So we're looking for E, where a negative charge Q of 3 times 10 to the negative 7 coulombs experiences a force of 9 newtons. So we're looking for E. I have a charge of negative 3 times 10 to the negative 7 coulombs, and you have a force of 0.09 newtons. Now here's my charge. All right. And you're going to be some distance, excuse me, it is moving in some electric field, and it will experience some force. And I know that the force is QE. The relationship between force, the charge, and an electric field, and the electric field is F is QE. So E is F divided by Q. So it's 0.09 divided by negative 3 times 10 to the negative 7. And this gives you a negative 3 times 10 to the 5th newtons per coulomb. Now, if the electric field, E, is 2.1 times 10 to the negative 5 newtons per coulomb, and a charge is 2.3 times 10 to the negative 19, what's the distance that charge is away? So in this case, you have a charge, you're a distance d away from that charge, and you're measuring the electric field. So we know let's write out our givens. E is 2.1 times 10 to the 5th newtons per coulomb. Q is 2.3 times 10 to the negative 19 coulombs. We're looking for D. Now I know E is KQ over D squared. So we need to solve this whole thing for D. To solve it for D, first we have to get D out of the denominator, so we multiply through by D squared. So E D squared is KQ. Now I need to get E to the other side because it's being multiplied. I'm going to divide it. So we get D squared is KQ over E. Now I want D completely by itself, so I'm going to square root it. So D is the square root of KQ over E. All right, now let's plug these in. D is the square root of 9 times 10 to the 9th. Q is 2.3 times 10 to the negative 19 divided by, let's say, E is 2.1 times 10 to the negative 5. And you wind up getting 0.00993 meters. Now, what if you have an electric field of 3.2 times 10 to the negative 3 newtons per coulomb? And in this case, we give you D, it's 0.005 meters. What's the charge? Okay, we're looking for Q. It's the same situation. You have Q, you're a distance D away from it. It has some strength of electric field. And I know E is K Q over D squared. So let's solve this for Q. I've got to get rid of my denominator. Always get rid of your denominator. So multiply through by D squared. So E D squared is KQ. We're still looking for Q, so we're going to divide both sides through by K. Let me switch my pen color here. Divide by K. So Q is E D squared divided by K. All right, so the charge we're looking for is 3.2 times 10 to the negative 3 D squared, so it's 0.005, and remember to square that, divided by 9 times 10 to the ninth. Multiply straight across, and then divide, and you get 8.89 times 10 to the negative 18 coulombs. Now I have a negative charge. Q is negative 2 times 10 to the negative 8th coulombs. Experiences a force, F, 0.06 newtons, to the right in electric field. So here's my charge, and its force is to the right. My charge is negative. What's the magnitude of the field? Well, I know the relationship between force, field, and charge is F is QE. So E has got to be F divided by Q. So it's 0.06 newtons divided by negative 2 times 10 to the negative 8. Now they ask for magnitude, so I can drop the negative sign. And I'm going to get 3 times 10 to the 6 newtons per coulomb. Instead of using the negative sign here, let's use my diagram to find the direction. The negative sign is going to tell me it's in the opposite direction. If I had a positive charge and I had a force going to the right, that would tell me my electric field is to the right. But because I have a negative charge and the force is going to the right, that tells me the electric field is to the left. Now, a positive charge of Q is 5 times 10 to the negative 4 coulombs is an electric field that exerts a force of 2.5 times 10 to the negative 4 to the left. What's the magnitude of the electric field at the location? Okay. I'm going to have a little bit of trouble with room here. Q is 5 times 10 to the negative 4 coulombs, and it's positive. And F is 2.5 times 10 to the negative 4. And we'll deal with the directions down here. All right. What is the electric field at that point? F is QE. So E is F divided by Q. So it's 2.5 times 10 to the negative 4 newtons divided by 5 times 10 to the negative 4 coulombs. And so we get an electric field of 0.5 newtons per coulomb. What's the direction of the electric field of the test charge? Let's see, I have a positive charge. All right. It's an electric field, and the force is to the left. Okay, because the force is to the left, that tells me the electric field is to the left because I have a positive charge. If the test charge was moved closer to the center of the field, how would the magnitude of the force change? Well, it would go up, because as the electric field goes up, the force is going to go up. So we'll put increase. All right, now there's a mistake in this one. I'm going to do it both ways, but the answer given, obviously we're not looking for energy. Oh goodness, we're dragging along here. Let's go ahead and erase that. All right. Now, let's go back to pen. Okay, a force of 0.053 newtons is required to move a charge of 3.037 microcoulombs, a distance of 25 centimeters in an electric field. What's the change? Let's just find the change in potential, since that's the answer here. Let's write out our givens. F is 0.053 newtons, and the charge is 0.037 times 10 to the negative 6 coulombs. And the distance it's going to cover is 25 centimeters, and we're going to convert that onto meters, 0.25 meters. What is the change in potential? Well, this one's got multiple steps. I'm looking for V, and I know V is ED. I have D, but I don't have E. But look at this, I have F and Q. And I know that F is QE. So I'm going to solve this for E. E is F divided by Q. Now I'm going to take this E right here, and I'm going to plug it into this formula right here. So another way to write V is F D divided by Q. Now, this is work, isn't it? Work divided by charge. Well, gee, we already knew this. We haven't quite seen it in this form in this unit yet. So the force is 0.053. The distance covered is 0.25 divided by the charge of 0.037 times 10 to the negative 6 coulombs. And that gives me an answer of 3.58 times 10 to the 5th volts. Now, I'm going to do a double problem here, all right? Because, oh, that's yellow. That's not very colorful, is it? Can't see it there. All right. Now, we're going to pretend like we're answering the question asked. What's a change in potential energy? Okay. I know the change in potential energy is what? If you go back and, oops, you think about it, potential energy is the work done, correct? So there are actually a couple ways we could do this. We could do it the easy way. We do its force times distance. Okay, you can do it this way, and the force is 0.053 times the distance traveled, which is 0.25. Oh, sorry, my pen is having a hard day here. It needs a cup of coffee, or maybe it had too much coffee. 0.25. All right, so let me multiply that out. 0.053 times 0.25 is 0.1325 joules. Then we're going to hang on to this answer. That's a joules. All right. Let's do it using change in potential energy is QED. Excuse me. All right. So the charge is 0.037 times 10 to the negative 6. Now we already calculated the electric field is the force per unit charge. We could have calculated the electric field, couldn't we? The force is 0.053 divided by the charge, which is 0.037 times 10 to the negative 6. And then the distance is, of course, 0.25. And lo and behold, we get the exact same answer, 0.01325 joules. Be careful with these problems because sometimes there are multiple ways to do them. Now, how much work is done to transfer 15.15 coulombs of charge through a potential difference of 9 volts? Remember the definition, delta V is a change in potential energy per unit charge, and we know that that is also the work per charge. Oh, forgot my givens. Q is 0.15 coulombs, and the voltage is 9 volts, and we're looking for the work. So the work is going to be the change in potential times the charge, and I know I'm getting sloppy with my deltas. So it's 9 times 0.15, or 1.35 joules. Now, the electric field intensity between two charged plates is 1.5 times 10 to the third newtons per coulomb. And the plates are 0.08 meters apart. What's the potential difference between the plates? Well, E is 1.5 times 10 to the third newtons per coulomb. And the distance between them is 0.08 meters. And we're looking for the voltage, or the potential difference. VED, remember that, V equals ED. So the voltage is going to be 1.5 times 10 to the third times 0.08, or 120 volts. Wrong way. Now, if I have 13 joules of work done on 15 coulombs of charge, what force is applied to get it to move half a meter? Well, this is the work, this is charge, and this is the distance. So Q is 15 coulombs. Distance is 0.5 meters. Oh, and I forgot my work. Work is 13 joules. I know work is force through a distance. So the force has to be the work divided by the distance. So it's 13 joules divided by 0.5, or 26 newtons. What's the change in potential energy of the charged particle? Well, we know the change in potential energy is going to be the work done. So it's got to be 13 joules. What potential difference did the charge move? Well, I know the definition of delta V is a change in potential energy per unit charge. So it's going to be 13 joules divided by the charge of 15 coulombs. So that's 0.867 volts. Now, a capacitor has a capacitance of 2 farads. Once again, this answer is incorrect. So the capacitance is 2 farads. What's the potential difference? So we're looking for V. If you have a charge Q of 3 coulombs. Okay, I know Q equals CV. So V is Q divided by C. Q is 3 coulombs. C is 2 farads. F, make it a capital F. So this is 1.5 volts. A capacitor of 1 microfarad. So my capacitance is 1 microfarad. Remember that's 1 times 10 to the negative 6 farads. Has a potential difference, V, of 4 times 10 to the negative 5 volts. What's the charge? I'm looking for Q, and I know Q is equal to CV. Well, C is 10 to the negative 6, and the voltage is 4 times 10 to the negative 5. So this becomes 4 times 10 to the negative 11 coulombs. Now keep all these C's straight. I know it's confusing. one more. What's a capacitance? If 1 volt holds a capacitor, if you have 1 volt, so the voltage is 1 volt, and the charge is 6 microcoulombs, or 6 times 10 to the negative 6 coulombs. I know Q is equal to CV, and I'm looking for the capacitance. So the capacitance is Q divided by V, so it is 6 times 10 to the negative 6 coulombs divided by 1 volt, or 6 times 10 to the negative 6 farads. You can't just go jump into your answers. Good luck on the test.